Alright, this is our second video that deals with adding vectors. It's going to be the exact same question, only I'm going to use a different strategery in order to solve it. So it's going to be the same softball, same 65 miles an hour, same direction, same wind blowing, same direction, only I'm not going to mess with rulers and protractors. That was for the graphical method. What I'm going to show you now is how to do it with components, meaning you don't need those. But what you do need is a magic box so you can push the sine, the cosine, and ultimately we're going to lay out at night. All right, so I'm going to erase the diagram we made and just sketch what would a 35-degree east of north arrow look like. I don't know, it might look something like yay. So this is what I'm going to call vector 1, the softball itself. It went 35 degrees east of north. That second letter N tells you that we're going to go from north 35 degrees. So this arrow now, we're going to turn it to a triangle. All right, that one has the hypotenuse, 35 degrees. The hypotenuse is 60 miles per hour. To turn it into a triangle, you know, there's 3 sides to every triangle. All right, now we got this one. We need the horizontal and vertical components, the x and the y. So when you draw your vector, now you have options. Do I want to go up in the y and then over in the x? Or do I want to go over first and then up to draw a triangle? And the way you answer that question is look at the second letter. That is your reference direction, and since our second letter is north, we know we're 35 degrees east of north. So that north is going to be our reference line. The angle I know is right there, so I am going to, in this example, go up and then over. So the blue one is the y component. The green one is the x component of that triangle. So now I have a velocity in the y for the first vector and a velocity in the x of the first vector, vy1, vx1. All right, now what I'm going to do is the exact same thing for the second vector. The 15 mile per hour one, 10 degrees south of west. So all right, what would a 10 degrees south of west arrow look like? South of west, not a whole lot south of west, so I don't know, maybe something about yay. It doesn't have to be to scale, it doesn't matter, just draw a sketch of what that angle would look like, of what that arrow. That very shallow angle there, 10 degrees, that one, very shallow because we are only 10 south of west, so our reference angle then is from due west. Again, that second letter tells you, all right, I'm going to go over and then down instead of down and then over. So the triangle that I will end up with will have an x component that goes from there to there. So there's a velocity x of the second vector. I'm going to call it vx2. And then straight down from there right here is the velocity of the second vector in the y direction, so I will call that vy2. Okay, and again, that hypotenuse was 15 miles per hour. All right, so now what I have are the 2 triangles broken down into x's and y's, and now we can literally just push the plus button. What I'm going to do is combine this green arrow with that green arrow to get a sum of the velocities in the x. Then I'm going to combine this blue arrow with that blue arrow to get a sum of the velocities in the y. Just combine the 2 x's and combine the 2 y's. So in order to calculate those, the vx, I mean I might as well start with x, it doesn't matter, but that green line is opposite the angle that we know relative to the hypotenuse. So since we're opposite the angle we know, I'm going to use the sine button. And so for vx1, it's going to be the sine of 35 is equal to our velocity in the x of the first arrow divided by the hypotenuse of 60 miles per hour. So to solve for the velocity of the x component, I'm going to multiply by 60. So the Vx of the first vector is 60 miles per hour times the sine of 35 degrees. And that'll equal something, I don't know yet. If the x then is opposite that angle, then the y is adjacent to it. So this blue line is adjacent to that 35. So there's your in ca. So there's the adjacent. So anyway, if the sine of 35 was our x, then the cosine of 35 is going to be our y. So the Vy1 is 60 miles per hour times the cos of 35 degrees, and that will equal something else. All right, so then it's just time to start pushing buttons and make sure I'm in degree mode, which I am. So 60 sin 35, 60 sin 35, boom, and 60 cos 35, boom. All right, the 60 sin 35 is 34-ish, 34.4 miles per hour. So that's what this x component is now, 34.4 miles per hour. All right, and the y one is 60 times the cos 35. That was the 49.1 miles per hour. So this one, 49.1 miles per hour. Okay, so to those two numbers, this green one I'm going to then combine with that green one. And then this blue one I'm going to combine with that blue one. So to do the math on this triangle, to do the x now, the x is adjacent in this case. So we have a cosine function for the x. So the cos of 10 degrees for this particular triangle is the same thing as the adjacent angle, that's the v, or adjacent side, sorry, the Vx2 over the hypotenuse, which is 15 miles per hour. So our velocity in the x of the second vector is 15 miles per hour times the cos of 10 degrees. And again, we can do the same relationship. We say, well, since the x is adjacent, then the y is opposite. So if the x was a cosine, the y is going to be a sine. So the Vy of the second vector is 15 miles per hour times the sine of 10 degrees. So now again, we're ready to just push buttons. It's that simple. So I'm going to take 15 times the cos, 10, boom, get a number, and then 15 times the sine of 10 and get another number. All right, so the Vx2, 15 cos 10 degrees. That quantity ended up being 14.8. It really didn't change much, and that makes sense because 10 degrees is a very small angle. All right, and Vy is 15 times the sine of 10, and that is a very small number also. The Vy2 ended up being 2.6 miles per hour, and that makes sense because if it's only 10 degrees, it's a whole lot of x, not a lot of y. All right? So now, we have to then double check a few things. First of all, if we only had a sign, meaning, all right, when we combine and push the plus button, are we going to push the plus button or are we going to push the minus button? Since this green arrow in the x is to the right, that 34 is to the positive direction. So this 34.4 is a positive number. Then when you compare that to this green arrow for the second triangle, that green arrow is pointing to the left, which is clearly in the negative direction. So this 14.8 is a negative number. So when I combine them and push the plus button, I'm going to actually push the minus button. And the same thing with the blue arrows, because this y is straight up, that's Paula Abdul, 49.1 miles per hour. That's in the positive y, and then in the negative y, 2.6. So since this one's pointing down, when we push the plus button for the y's, then those will clearly be subtracted as well. All right, so then what we're ready to do is Pythagorean. We're going to take this one and this one, turn it into one y arrow, take the two green ones, turn them into one x arrow, all right? And I need to give myself some room here, so what I'm going to do, since I have that written and that written, Vx2, I'm going to rewrite up here, that was negative 14.8. Vy2 was negative 2.6. Then I need to get rid of this so I can draw my last triangle, which is the sum of the x and sum of the y. So, sum of the y's are 49.1 minus, in this case, 2.6. And then the sum of the x's are 34.4 minus 14.8. All right? All right, so yay, magic boxes. 49.1 minus 2.6 is clearly 46.5, so we got 46.5. That's our net y velocity. Our net x velocity, 34.4 minus 14.8 is clearly 19.6. That's our net x. So what I'm going to do now is make a triangle with this as the y and that as the x. And it doesn't matter which one you start with. So the net y, I'm going to rewrite because I'm going to have to use this space again. The net y, 46.5, and the net x, 19.6. All I wanted to do is write that down so we can go and draw our last triangle. So the y is positive 46.5. So I'm going to start down there and go Paul Abdul straight up, 46.5. Then I'm going to go tail to tip, right? 19.6, that's a positive x. So now I am going to go tail to tip, 19.6. That way, 19.6. That's in the positive x direction. So now I'm ready to get the resultant, and the resultant is tail of where you started to tip of where you ended. To get the magnitude of the resultant, the r, that's what we're looking for, we just Pythagorate this. All you do is 46.5 squared plus 19.6 squared, square rooted. So I push the square root button first, and I recommend you do that too. 46.5 squared plus 19.6 squared, and it's clearly 50.46, 50.5-ish miles per hour is the resultant. And that's good because last time when we did this with the tail to tip method, we got a number that's very, very, very similar to 50. And then the angle. What direction is this guy pointing? In order to get the angle, you then say, all right, compared to that, again, you draw that line relative to north, south, east, or west. Since the blue line is already straight up due north, what we're going to do is say we're east of north. I'm gonna do what I call layout at night. That means I'm going to push an inverse tan button, 19.6 divided by 46.5. So I'm going to say that angle is the inverse tan. That's what I make the joke, layout at night. Inverse tan, 19.6 divided by 46.5. So second tan, 19.6 divided by 46.5. And this is what, 22-ish, 0.8 degrees, 22.8 degrees. That is then east of north. Alright, so that angle I like a little better. Component-wise, it's all just pushing buttons. Don't worry about drawing it to scale. You're just sketching. The overall strategy is break each arrow into triangles. They have an X and a Y component. So find the components of each one and then add the two components together. So this Y added to that Y is clearly a subtraction. This X added to that X is clearly another subtraction. Whatever those two are is what you make your final triangle out of. This triangle is the net Y and the net X put together. When you have that, then you're ready to Pythagorate, which means push the square root button. Once you have that, 50.5, and lay out at night. So the last two steps again, get Pythagoras on the phone, lay out at night. This is the component method, all right? It's a little more mathemological, but it saves you from having to play with rulers and protractors, and it is a little more precise. The angle we got from the last one was dancing around, what, 23-ish? And so that's pretty good. So those answers are pretty darn similar. All right, so this is components, and hey, you now have direction, don't you?